Good afternoon and welcome back. We have 3 presentations scheduled for this session, the sponsors being Amazon and AWS. A quick reminder before we begin with the presentations, there will be time for question and answers after each presentation. For our live audience, if you have any questions, please raise your hands and I'll bring the mic to you. This is so that our online audience can hear your questions as well. And for our online audience, if you have any questions, please type them in the chat window and we'll get to them. I'll hand it over to the team now.
Hello, and thank you for joining us this afternoon. We are Team CS2301 with Amazon Alexa. Today, we'll be presenting our capstone project. Now, before we get started, this presentation does contain profanity. So if you feel uncomfortable, please feel free to exit the room at any time. During this presentation, we'll be covering an overview of our project, accomplishments, and challenges, followed by an interactive demo. And then we'll also follow up with our plans moving forward, as well as the impact of our project. My name is Gary Tu.
My name is Isabella Wallace.
My name is William Somat.
I'm Jacob. I'm Blaise Naranyabagira.
And for the rest of our team, we have Sheila, who is our faculty advisor here at Seattle University, along with our primary sponsor at Amazon Alexa, Sundar, who's the principal PMT for Alexa's experiences. And we also have our stakeholder, Roshanak, who is also a principal PMT for Amazon Alexa Experience. And she was also the department chair of CS a few years back. We welcome you back. And we also have our 2 primary engineering contacts, Vijay and Vishan.
Our sponsor is Amazon, the creator of Alexa. We are part of the trust and privacy team, specifically ASCII, Alexa's Sensitive Content Intelligence. And ASCII is responsible for filtering out responses and identifying sensitive contents within Alexa's traffic. Alexa have many different devices. Some are auditory only, such as the Alexa Dot, and some are auditory and visual, such as the Alexa Show. Amazon Alexa may use contents outside of Amazon, such as the internet, news articles, blog posts, YouTube, or other user-generated contents, and it may contain the use of profane words. Amazon wants to prevent Alexa from using or showing the profane words to customers because Amazon wants to avoid headlines like these, where a kid asked Alexa for a TikTok challenge and Alexa responded with a dangerous TikTok challenge, or another where a man claimed that Alexa was swearing at him.
And so why focus on this opportunity? Well, by minimizing sensitive content and profanity that is used in Alexa's answers, we maintain customer trust and increase customer trust. Additionally, we want to preserve and maintain the brand reputation. And all in all, we want to continue to foster and improve positive customer experience with Amazon Alexa.
Our project has 2 main objectives. The first one is to detect variations of disallowed words and phrases, such as duplicate of letters or misspelling of letters. And examples of that can be seen here on the screen. The second one is to detect vulgar-sounding phonetic pronunciations of phrases. An example of that would be taking the words sofa and king. With phonetic sounding, it might sound like so fucking instead of sofa and king separately. For our solution, we created an API, an application programming interface, and we designed it to detect text-based sensitive content inputs. And we designed it using Go language. And the way we do that is through these 6 use cases that we came up with. We want to be able to detect profane words with minor misspelling of letters. We want to be able to detect profane words with all 3 levels of lead speak, and we'll get into that at a later slide. We want to be able to detect profane words with duplicate of letters. And we also want to be able to detect profane words with phonetic sounding contents. Lastly, our design will return a Boolean value with its offending contents and its policy violation.
So for our deliverables, on top of the API, we have to deliver the GitHub repository for our code. And on top of that, we have to deliver our documentation so the stakeholders or any other internal Amazon teams can go through the code, understand our approach, and maybe later improve our system. We broke down the project in 3 major milestones, and those 3 milestones were accordingly matched with the 3 quarters of the year. For fourth quarter and the first milestone, we have creating the documentation for the project and all the planning documentation, and setting up our backlog with the tasks based on our use cases. For the second quarter, we have solving the first 5 use cases. That means misspelling, duplicates, and lead speak, and setting up unit testing. For the third quarter, we have our third milestone, which was about solving phonetics, and then creating the project day deliverables, and also doing more documentation about the API. When it comes to project methodology, we adopted agile principles. We broke down our project into 12 sprints. Each sprint was 2 weeks long, and our backlog tasks were all based on the 6 use cases that we defined.
Yes, I'll go over use cases 1 through 5. So the primary goal of it was for number 1, to detect leet speak. And for reference, leet speak is sort of this internet slang way of typing and spelling things. And so it has 3 different levels. Level 1, you replace pronouns with numbers. Level 2, you go a little bit higher and you pronounce consonants with numbers and symbols. And then level 3, you combine 1 and 2, and then you also just sort of start replacing anything with everything, and it gets really complicated. We also have misspelled words and repeated letters, which are also goals of 1 through 5.
So when it comes to solving use cases 1 through 5, which are leet speak, misspelled words, and duplicate letters, we need to understand the similarity between words. So for example, if we have the words cat and rat, we want to quantify how similar they are. To do this, we use Levenshtein's distance algorithm. Levenshtein's distance is an algorithm that computes the edit distance between 2 words. This is the number of modifications, such as insertions, deletions, or replacements necessary to transform one word to another. So for example, the edit distance of cat and rat would be 1 because you just need to change the C to an R. Now, we want to use this to transform each word in Alexa's traffic to a list of known profanity. And using Levenshtein's distance, we can create a scoring system, which represents the similarity between words. This is essentially the percentage of similar characters within the 2 words, and a score of 1 would mean that they're identical. However, before computing the score, we need to do some pre-processing first. And that's mainly because of our use case 5, which is repeating characters. For example, if you have the word shit with 20 T's, it'll have a great distance compared to shit properly spelled. So we remove any 3 or more consecutive repeating characters and reduce it down to 1 instance. And that's because in the English language, there's a rule where words cannot have more than 2 instances of repeating consecutive letters. So this cleaned version, which also has punctuations removed, is then given to our scoring system. And when it comes to phonetics, which is our use case 6, we need to understand how similar 2 words are phonetically. And for this, a lot of phonetic algorithms will give us the phonetic representation of words. And we use them because a lot of them were developed specifically for English or Latin-based languages. And many of them were also made for matching names.
And so there's a variety of phonetic algorithms we decided to look at when trying to look at our use case 6. And so we focused on 16 different phonetic algorithms, as you can see here. And there were a couple of factors we were going to look at to review these phonetic algorithms in order to choose some to implement. And so one of the factors that we looked at was fuzziness. And Jacob will discuss about what fuzziness is when it comes to a phonetic algorithm.
Yeah, so fuzziness was a very big key player in our phonetic algorithm. And so what fuzziness is essentially how much you approximate the phonetic representation of a word. And so if you have a word that is too fuzzy, you'll get false positives. So for example, if bitch equals witch, that is a false positive, you don't want that. But you can also get vice versa, where if it's not fuzzy enough, you'll get false negatives where FUCK does not equal FPHUCK, where they should be pronounced phonetically the same, but if it's not fuzzy enough, then you'll get a mismatch.
So this is our 3 phonetic algorithms that we chose. Keep in mind that for our phonetic package, an input would have to be detected by all 3 phonetic algorithms for it to work. If not, it will pass through undetected. The first one is the double metaphone algorithm, and this algorithm is based off of the original metaphone algorithm, and it is best used for single words based on their pronunciation. The second one is the New York algorithm. This algorithm was originally created for detecting names for the state of New York, but it can be used for other things such as substrings, phrases, and single words as well. The last one is the Cologne phonetics algorithm. This is an open source algorithm that is used to encode words based on their pronunciation. This algorithm assigns words to a sequence of digits, and it can also make identical sounding words to have the same sequence or codes.
Okay, so I'll go over our high-level architecture diagram. So at the top left, it all starts with the customer, and when they ask Alexa a question, that question will then get routed into internal Amazon Alexa traffic. And within that traffic, eventually it'll reach the ASCII team, and the ASCII team is responsible for removing profanity. So then they will contact our API, which is on the right side. And from our API at the top is the detect package, which is the main orchestrator package. And it orchestrates the lead speak and the phonetic package. And the lead speak package is responsible for catching variations of profanity. And the phonetic package is responsible for detecting phonetic variations of profanity. And at the bottom of it, we have our dictionary, which both packages interface with, which defines what profanity actually is. And in a larger scope, we have the possibility of interacting with other Amazon services that also need profanity detection.
So blockers, we were lucky to not run into many of them, but obviously we couldn't escape all of them. We had 2 major blockers, and we are a competent team, we were able to overcome them. So our first major blocker was the fact that we were facing a limited data for testing, due to the fact that in this kind of domain, most data is just private for most companies. So our solution was to just generate our own data. So we created our own data sets, and that's what we used to test our features. Our second blocker was that we were wishing to deploy this system on the internal Amazon infrastructure, and that's the AWS. But due to the time requirements that it took, and we did not have that time on our hands, so we just left that task to the internal Amazon team and just submit our system the way it is. We are happy to announce that we're able to complete all our milestones. That means we're able to create the REST API. We're able to solve all of our use cases. That's misspelling, duplicates, lead speak, and phonetics. We are also able to set up automated testing. On top of that, we were able to create a website where we can demonstrate our service capabilities.
Alrighty, yeah, so it's time for the demo. So if you happen to have your laptop with you, now's a great time to pull it out. Otherwise, you can take your phone and scan this QR code here. The URL is amazon.garrett2.com. It's also written on the whiteboards too. I'll give you guys a second to do that. Alrighty, so this here is what the website looks like. So as you can see, we have a text input. Within this text input, you can put anything you'd like, including profanity or variations of profanity. And if we scroll down and click this Detect Profanity button, we'll see that instances of profanity have been detected. And if we were to click on the highlighted profanity, we can see how it was detected. So for example, this specific instance here was detected by both the phonetic and leet speak strategies that we have within our code base. And while testing, we also love to run longer content through it. So for example, Wolf of Wall Street has a ton of profanity in it. So if we were to copy and paste that in and run it, we can see that there are many instances of profanity that were detected by our system. Amazon had a goal for us to respond within 40 milliseconds for normal Amazon traffic, which are short questions. or short responses. However, even for the super long movie script, we can see that it's responded within 100 milliseconds, which is relatively quick. And that concludes this demonstration. You guys can continue playing along on your phones.
So with all that, to wrap up, we had a lot of major lessons and advice to any future capstone students that I do see here. And so I'll just talk about this first one right here is visibility of your teammates' work and just making sure that you and your sponsor and your advisor are all on the same page on what tasks are being done, who is doing them, what the progress is, and additionally just having that transparency. It just allows you to advocate for yourself. It allows you to advocate for your teammates, allows you to advocate your team to your sponsor, because there might be a disconnect between what your sponsor wants and what the team is able to produce in whatever deadline you have. And so just making sure that everyone is on the same page on the work that you are doing can just ultimately lead to high quality work.
So for future recommendations for the project, our first is more research into phonetic algorithms. We covered a lot of them, but there's still more out there, and also maybe a deeper analytical approach to the ones that we did find success in. Number 2 would be lemmonization. Lemmonization is the act of removing suffixes from words. It's like ing, ed, er. And so when you remove these from words, it sort of standardizes them and helps prevent false positives, false negatives, and improves performance. And lastly, we have machine learning. Our phonetic solution feels like we're trying to fit a square peg into a round hole, and it just doesn't really feel like the correct solution. So we think perhaps a more dynamic approach with machine learning would fit the problem better. For what's next, we have to turn over our project deliverables to Amazon. They can figure out how they want to incorporate into the Amazon Alexa framework, and also more research into phonetics, as I said.
Thank you for joining us today. That concludes our presentation, and we'd be happy to take any questions.
You had 16 phonetic algorithms that you initially looked into. How did you choose 3 to continue with?
So we had 3 main factors that we looked at. So the first one that we decided to touch upon was fuzziness, and that Jacob explained. It was how stringent or lax the algorithm was when comparing 2 different sounding syllables. Another factor was the type of result the phonetic algorithm returned. So during our research, we discovered that there was 2 different types of phonetic algorithms. There are string results algorithms, and hash results algorithms. The issue with hash results algorithms is that you cannot use it to do comparisons with like a similar comparison. With hash base, it was like a string of words or a string of numbers, or sometimes a mixture of characters and numbers. And you can't, with a hash-based algorithm, you can't really quantify how similar one output of the phonetic spelling of one word compared to another word with those types of algorithms. You can do it with a string result, and that way we can use Levenshtein's distance, which we already use, as a way to compare likeness between 2 phrases, 2 words, etc.
Yeah, and one way to think about this is that with string results, you get essentially a number of how similar they are, a number between 0 and 1. However, with hash-based results, you get a Boolean, which is a yes or no. There's no similarity. It's either it matches or it doesn't, which is not what we're looking for. String results give us more information.
So you said you had limited access to a data set and you generated your own data set yourselves. How did you generate your own data set yourself?
So we were able to scrape around the internet, and our stakeholders were able to provide us with a little bit of data. So we just build from that and build like sentences and try to expand all those words on top of words that were already existing from the dictionary. And that's how we just made our data sets.
And a follow-up question, right? With the data set and with the algorithms you use to test if a word was profane or not, right? Did you pick up alternative algorithms to sort of compare the effectiveness or the accuracy when you have a profane word?
Right, that's a great question. So with our data set, we had split the data set into two categories. We have positive cases and negative cases. So positive cases are cases where it should match. In other words, like FUCK and PHUCK that we saw on the screen earlier, that's a positive case, they should match. However, we also have negative cases where they should not match. So using these two categories, we're able to compute the false positive, false negative, true positive, true negative. And with that, we get the accuracy, recall, and precision. So these are metrics that we can use to determine how accurate each individual algorithm is.
So your data sets look to be like very standardized profane kind of use cases, right? But as we know that like within society, we have linguistics and it develops, and you know the content sensitivity looks to be tailored to maybe young kids, Gen Z, who are using maybe language that hasn't been so standard. What are like some considerations for future, I guess, developments of this API to account for the development of maybe slang words that younger people are using that maybe people who are older might not be able to recognize and thus not implement and consider going forward?
Yeah, so currently we just have like a list of profane terms, and you can really update it whenever you want. So I suppose someone at Amazon would be responsible of taking charge of what they consider profane and not. And that's sort of more of like a long-term issue, I guess, more than like a design one for us currently.
As a follow-up to that, do you foresee it causing issues with, I guess in your example, but bitch and witch, right? The idea of like witch is not necessarily something that is foreseen as like a negative term, but with the development of language, maybe as like young slang might see it, it could be used as like, hey, sick is like, it's a negative like connotation, like something is sick versus like, hey, this is really sick. Like, how are we able to like differentiate between like that kind of barrier?
Yeah, that's a great question. So with our program, we have two data sets, and one of them is a list of profanity. And if I'm able to share this, the current Amazon implementation is a list of rules. They're all it's both ML and rule based. So right now, if there is a case where that needs to be filtered, we would need to add a new rule. So that's kind of similar to what we have going on here, except ours is able to take multiple variations of it.
It is time for us to move on to the next presentation. Let's thank the team.